Okay, today we're going to begin the topic of acids and bases, and we will tie these back into equilibrium because we're going to see that we have strong acids and we have weak acids and strong bases and weak bases, and the weak ones actually get into a point of equilibrium, and that's where we're going to tie that in to the equilibrium unit. Okay, so let's get in what an acid and a base is. So common acids are like vinegar, that has acetic acid in it, and you've got like ascorbic acid, vitamin C, and citric acid, hydrochloric acid in your stomach. Sodium hydroxide is in Drano. That's a base. So let's look at some definitions, and I do expect you to know these definitions for your test. So we've got three different definitions that we're going to look at for an acid. First, we begin with Arrhenius. Arrhenius says that an acid is anything that is going to actually produce a hydrogen ion, or also known as a hydronium ion, if you were to put it in water. So the minute you put it in water, the hydrogen ion will come off and it will attach itself to a water molecule. For example, HCl is hydrochloric acid. If I take HCl and I put it in water, the hydrogen is going to come off of the chloride ion and it attaches itself to a water molecule, and it makes this substance called hydronium, which is water with an extra hydrogen, so it's a charged particle. So you're going to get hydronium ions floating around and then chloride ions floating around. Another way to write this is to already assume that we're going to put this in water, HCl, hydrochloric acid, aqueous, put it in water, and it breaks down into hydrogen ions and chloride ions. So this hydronium and H plus are really like synonyms of one another. This one's just not showing the water molecule. Technically with aqueous it is. This hydrogen automatically attaches itself to a water molecule. So these are the same thing. Now I'm a little bit on the lazy side, so I tend to write it like this. Okay, so that's Arrhenius. The hydrogen ion is going to come off, attach itself to a water molecule. Alright, Bronsted-Lowry is very similar in definition. It just doesn't really bring the water into play. It says an acid is anything that is going to donate a hydrogen atom. Ion, not atom, but ion. We say it's a proton donor. Proton, an H plus ion is the same thing as a proton, because if you think of hydrogen, it has one proton. It really has no neutrons. Most of them don't. The most common isotope, and it has one little electron. So one proton, one electron for normal hydrogen atom, but it becomes an ion when it loses this electron, a positive one, cation. It loses that, and when that happens, all it is a proton. So that's why proton and H plus are actually said to be the same thing there. So that's the Bronsted-Lowry definition. It's going to donate a H plus. It usually will donate that to some other thing that acts as a base, and we're going to see that the base is going to accept that. And then we get to the last one. Lewis, remember Lewis is the gentleman that did the Lewis dot diagram, and those dots again were electrons. So his definition concentrates on the electrons, and it has to do with accepting a pair of electrons. So I'll go ahead and show you this definition. You'll really deal more with this one in organic. So it'll explain in organic why some things are considered an acid. You're like, oh, that doesn't look like it should be an acid, and it's because of that lone pair of electrons that it's going to donate in that reaction. So I'll go ahead and just introduce it, but we're really going to stay in Arrhenius and Bronsted-Lowry as far as our definition is concerned in Gen Chem. Alright, so some of the characteristics, and I do want you to know these as well. In fact, on your test, I'll give you some of these characteristics, and you'll have to tell me, is this an acid characteristic, a base characteristic, or is it both? Okay, and we're going to see some of these in lab as well. So if we were to taste, we don't taste anything in lab, but if you were to taste, acids do have a sour taste. Even hydrochloric acid, our stomach acid, has a sour taste to it. So if you've ever regurgitated, you've actually tasted it. We're going to see in lab that in an active metal, remember the active metals are the alkali and the alkaline earth metals. They are said to be the active families in there. So if we take something and we put one of those active metals in an acid, it's going to give off hydrogen gas. And we're going to do that in lab. You're going to see that. It also conducts electric current. So it's an electrolyte from Chem 1. It is going to light up that light bulb. It's going to turn litmus paper red. Litmus paper has an indicator soaked in it, and so it will change red color. It's more of a pink color, but we say red, so it's red if it's an acid. In lab, we're going to deal with an indicator called phenolphthalein, and phenolphthalein turns, if it's a really strong acid, it actually will turn cloudy white, but it's really kind of a clear in an acid. So this one's kind of unique for acids, because most of the time we think pinks and stuff, but this one's actually going to be clear. And then one of our cheaper indicators is red cabbage, and it turns a reddish pink color in red cabbage. And then it has a pH of less than 7. So the lower numbers are acids, less than 7 on the pH scale. So this is from Chem 1, but just in case, Gen Chem 1, just in case you don't remember or you never learned how to name an acid, if you have what we call a binary acid or an acid that doesn't contain oxygen, if it doesn't contain oxygen, you're going to use the prefix hydro. Well, you're just going to have a high old time, aren't you? So we're going to use hydro. And then you use the part of this word, and that's bromine, but we're going to say brome, and then it's ic, so hydrobromic acid, as long as there's no oxygen involved. This is hydro, that's chlorine, so it's chloric acid, hydrochloric acid. So if you see hydro, there's no oxygen involved. Cn is cyanide, so that's one of the polyatomic ions. This is hydro, Cn is cyanide, so cyanic acid. Hydrocyanic acid. Okay, so now what if it has an oxygen? If it has an oxygen, it's said to be a ternary acid, also called an oxyacid, and this is where knowing those polyatomics, I will upload that polyatomic sheet for you just in case you've misplaced yours. So this is where knowing those polyatomics are real important. NO3 is nitrate. NO3 is nitrate. So if it's an acid and it has a hydrogen, we change the ATE polyatomics to ic. There is no prefix on this one. So then this would just become nitric acid. Nitric acid. SO4 is sulfate. So you would think you would say sulfic acid, but for sulfur you actually put the UR back into it. So we say sulfuric acid. And as soon as that thing quits spinning, I will write sulfuric acid. There we go. Sulfuric acid. There we go. So sulfate becomes sulfuric acid, nitrate becomes nitric acid. The key word is they are ic with no prefix in the beginning. NO2 is nitrite. So if our polyatomic is an ITE, we change it to OUS. So this is actually nitrous acid. Nitrous acid. All your ITE or your OUS acids, none of them are strong acids, so OUSs are always going to be weak acids. So this is sulfite, so this is actually sulfurous acid. Just to remind you how to name acids. Okay, should have learned that in Gen Chem 1. Alright. I have just this picture because these are hydrangeas, and hydrangeas are actually natural indicators. And so if the soil is acidic, the flower will turn pink. If the soil is basic, the flower will turn blue. So this is the same plant. It's not two different versions of the plant. And if it's more of a neutral, you're going to start to see purple. So it's kind of like, can tell you a lot about the soil, which is cool. Alright, bases. Same three guys, different definition. Arrhenius says a base is going to produce hydroxide in water. So if something has a hydroxide and you put it in water, it's going to be a base, and that's why all of our hydroxides are bases. So sodium hydroxide, if we put it in water, it's going to give us sodium ions and hydroxide ions. Most of the time when we write this equation, we don't put the water in it, we just take it apart, because if you put the water in it, I should have put just aqueous there, that would have made sense. The water's here and the water's there, so water doesn't really react, it just separates those. So the most of the time we will just not put those waters in there, we'll just break it up there. And so Bronsted-Lowry says a base still has something to do with a proton, but before acids were proton donors, these are proton acceptors. They're going to pick up that hydrogen. So what happens is there's their acid here, and it's going to donate that hydrogen to this hydroxide, and that's where water is coming from, because water is like HOH, so you get a hydroxide and a hydrogen coming together to make water. And so this hydroxide, sodium hydroxide, is picking up that H, is what's happening in that reaction. And then Lewis again about the electrons, but this time is still about electrons, but bases actually donate. I'm going to show you this one just for because we're going to be dealing with ammonia as a base. I would like you to know ammonia is a base. If we drew this out there, that is that trigonal pyramidal, it's got that lone pair of electrons that actually donates in the reaction. So this is what makes that a base. And we're going to see that actually this in water is going to produce hydroxide as well. So ammonia, NH3, is a base. So it's a weak base, but I'm going to start you to learn that it's a base. So anytime you see ammonia, NH3, you'll know it's a base. So let's talk about the characteristics. You do need to know these two. They don't taste sour, they taste bitter. They do not react with the active metals. So if I were to put sodium and sodium hydroxide, we're not going to get a reaction. We're not going to get hydrogen gas forming. They do conduct electricity, so both of them will conduct electricity. They're going to turn litmus paper blue. Remember, blue for base. Weird thing is that phenolphthalein is going to turn pink, and we are going to use this guy in lab, which is the Y. So this is actually a liquid. This one's a paper, but this one's a liquid indicator, and it turns pink, and we're going to use it in lab, is why I want you to know that one. So the cabbage turns a yellowish green, kind of like a Shrekky color. We'll see that in lab as well. And it gets a pH of greater than 7. And it's actually slippery to the touch, and that's a characteristic because your soaps and things actually are bases that help break down the fats and things to get the oils and stuff when you wash your hands, etc. Please be washing your hands.